So I'm Simon Ceres. I have been running a little company called nymea for the last 10 years. And recently we had been acquired by ChargeByte. And what I and some colleagues have initiated is an open source software that does smart energy management. And the idea in teaming up with ChargeByte was, let's combine hardware, let's combine EVerest as state-of-the-art charging software, and let's combine it with a state-of-the-art energy management system. The energy management domain is something that has a couple of problems, because mostly you buy external hardware, you get an installer, the installer takes the hardware, puts it into your rack at home, has to configure it, and then this external hardware is an expensive piece of gear, and mostly it's a bit difficult to set it up and to operate it. What charger companies do nowadays is they sell additional hardware. So if you want, I will talk mostly about the residential application of solar charging, by the way, and how companies do it nowadays is they add an additional meter so they can measure the excessive energy. So that's one way how to do it, but you need additional hardware, you need an installer again, it's expensive, and it doesn't cover every use case, because a meter like that doesn't know anything about your solar system, about your home storage system and everything, stuff like that. The other way that it can go is an external hardware device. It's also a thing that doesn't really scale, so we don't see hundreds of thousands of energy management systems in people's homes, because it costs something, it's complex to install, and it's complex for the installer. Installers are not as innovative as we would like them to be, mostly. So the main idea was, now, today we have, anyway, Linux modules or Linux-based chargers. We can just use the software and install all the energy stuff directly onto the charger. What you need for that is a software, and so I would like to talk and introduce you to the nymea stack. Nymea stack is something sort of the home assistant in a commercial version, so it's a C++ embedded ready stack that can be integrated on basically every Linux device. And I can just quickly show it to you through an app how it looks like, because it's easy to explain by just showing the product. So first of all, what the stack does, so you have a server component that runs on the embedded device, and then you have a client. Client is just a visualization, what happens on the stack. So you can integrate the charger with many different other systems, third-party systems, like SMA, Huawei, Costal, PV stuff, metering stuff, even other chargers, smart meter tariffs, all this stuff. So if you want to connect to a Costal inverter, from the app you can just configure and install it, and then it works natively on the Modbus. Oh shit. Thanks. Ah, okay. Good hint. So again, the stack is simple from the end user or for the installer perspective. You can add any kind of device, like, as I said, solar inverters. Mostly it's about solar inverters and solar charging and meter devices, right? So you can connect to SMA, to Costal, to Huawei. So we have plenty of those inverters and meters integrated. When you did it, which is fairly simple, you just need an open Modbus connection on the inverter side. Then you have a basic app. This is, by the way, also open source, and it's a white label app. So if you happen to need an end user client, a smartphone app for your charger, then here it is, and it's quite simple to integrate. Then you have two options. You can either choose the charging current by yourself manually and pause the charging session, but the most important feature of the stack is energy management. So if you choose the eco mode, then you can start to, it is automatically charging using PV surplus, and I will show that to you quickly. I will just plug in the virtual car. So you can choose, like the user interaction is actually quite simple. You can say the state of charge that you have at the very moment. If we don't retrieve it from the charger by the ISO standard, the user can enter it manually, and then you say this is the target state of charge that I want to reach at a certain time. So if I want to leave tomorrow at 8 with 90%, then the system tries to charge every available excessive solar energy into the car's battery. The rest is done from the grid, even using a smart tariff, a dynamic tariff. And then on the energy stuff, so this is actually the most important stuff, the charger retrieves all the data from the existing solar system, like the PV production, the general consumption on the household, the state of charge of the home battery, and gives, so this is actually stored on the charger itself in the hardware and gives you all this nice history. So you have all the energy management and energy data stuff on your charger app itself, so you don't need the solar app actually anymore. That's basically it, simple as that. It's an added value and a nice feature on top of the existing charging hardware. So no hardware installation required, just a software add-on. This is the stuff that it works with right now. So it's Phronesis and Marcostal, Solar Edge, Huawei, Solax, and Watsonic. By the way, this is open source. You can go on GitHub and go into the code, check the quality. It's a commercial software environment if you want, so very well maintained, very well tested with hundreds of installations in the field. Soon we will introduce the spot market feature as well, so we don't just have the solar charging feature as a dynamic source of energy, we also have TIBA, or Octopus Energy, Avatar, and all those dynamic tariffs. They just add as a dynamic input, a dynamic energy source. And as I told already, with there is a simple to white label EVSE charging app. It's a very nice and user-friendly end user app to configure the charging point. Just as a quick overview how it actually works. The software stack sits in the middle. It gets the data from the solar. It gets the data through APIs from the grid, the spot market. It gets all the data from the user, like when do I want to be finished. And eventually it gets the data from the charger, from the car, state of charge. And this is all the data that is centrally managed. Technically, it's a daemon that runs on the device. It can be compiled for Yocto, Debian, whatever you want. Everything that is green is the daemon. It contains this device management layer, like you have all the device drivers that connect to the solar systems and all the third-party devices. It has a local database, can be a local database can have various interfaces. If you have to have a database on your system already, the daemon can integrate with existing database frameworks, and the logic Logic basically means the business logic to decide when to charge, when not to charge, and all that stuff. So now the most interesting part probably, we try to make this an EVerest module, or we try to create a very neatly interface so that the EVerest project and the nymea project work very seamless together, because we think that EVerest and the energy management stack together is a quite nice combination. I think it's an unbeatable charging stack, because EVerest has all the features, charging OCPP, the ISO, the DIN stuff. Our stack, which is also open source, has all the, let's say, the residential focused applications, and I think together it's a very powerful package. That's why we team up. Now, today, the stack is already commercially available, but we are thinking of ways in contributing the software stack into EVerest, make it part of the Linux Foundation, but this is all work in progress. Technically, I'm not an expert in EVerest yet, I'm learning a lot, but we think we're gonna hook up the nymea stack as an energy manager as a virtual fuse. So the energy manager says, I have 60 amperes max, and it just limits the EVerest stack to that numbers. Now it's a commercial application that is available in ChargeByte already. And I think that's it. If there are any questions, head to the website or head to Martin or myself. Thank you.
Thanks, Simon. I'm looking forward to having that in my house, an EVerest charger with an energy management system.
Yeah.
I should. Any questions for Simon? None? Oh, there. Yeah. Volkers.
Hi. Just one thing I missed. It's a module for EVerest, right?
Not yet.
But it's intended as a module of EVerest. But doesn't that require, that means that you would only support chargers that have a firmware based off EVerest, or am I missing something here?
It runs on the same, on the EVerest-based charger.
Yeah, so only chargers that run EVerest can support that module then?
Yes,
Okay.
yes.
Extra
So to be
selling point.
honest, we don't have yet figured out the best way to make an interface between those two daemons. These are two separated software entities on the same hardware stack, and we find the best link between those.
Thank you.
Any other questions? No? Oh, always miss people.
Hi. Is that supposed to work only for a single charger, or does nymea also support load balancing between multiple chargers?
It supports load balancing already, so I will just quickly go in the app and show it to you in. So basically what it is today is you can add as many chargers as you want, and in the user interface you can swipe between them, and the solar surplus or the surplus energy that is available is distributed amongst them. But we plan to add more features, so that this is what we have today, and it works. It's sort of a load balancer, but with the main focus of solar surplus energy. But throughout the year, so we have this on the roadmap for this year already, is a dynamic energy balancing feature that allows multiple chargers to automatically configure themselves, because we know the overall limit, and we try to make a load balancing feature that is free of configuration at all for a semi-public use case. So you won't need the app for that, but technically we have everything in place.
Okay, so nymea would run on multiple chargers, but there would be one superior process of managing.
Not necessarily. There can be a master charger, sort of, that runs the stack, and this can also interface to other chargers. Okay. But yeah, architecture-wise, it's not relevant.
Thanks.
Thank you. You talk a lot about the solar part and the, let's say, communication to the wall box or the charging system. Which protocols are you using here? That one which come from the manufacturer, let's say example Keba, or you use already OCPP?
Now we don't use OCPP actually for all the third-party integrations. We use the native API. This can, so for Fronius, for example, it's called Solar API. For SMA, it's called Speedwire. For Costal, Huawei stuff, it's Modbus TCP. So we made, main reason is OCPP is hard to configure for end users. This solution was established for the residential use case, so an end customer can use the app and configure the system himself.
Yes,
That's why we couldn't use OCPP. And all the third-party integrations have different interfaces. So
But are there, let's say, in the third-party world also wallboxes? You talk about solars and mostly. This is why I'm asking.
yeah, so you don't need to interface to another wallbox if you run on the wallbox, because internally you have the connection, right? The software stack runs next to the EVerest stack, so you have one enclosure, one wallbox, running those two software stacks. For the end user perspective, you have one app, one charger. You don't need to interface to other chargers. But it does not limit OCPP, of course. OCPP is a separate connection, and all the third-party energy management stuff is independent of that, uses different connections.
Thank you.
Then I have one question. That means the app connects locally to the Wi-Fi of the charger to work.
Yeah, it connects locally, but it can also connect outside the Wi-Fi using a remote proxy service. So the app tries to find the charger locally first. If it doesn't find it in your local Wi-Fi, then it just uses a small proxy server. But yeah, you can use it from everywhere.
Okay, thanks. No more questions? Then thank you.
Thank you.